NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
The spacecraft was launched over 46 years ago, but stopped sending data last November.
Launched over 4 decades ago, NASA's Voyager 1 probe embarked on a mission that would not only push the boundaries of human exploration, but redefine the scale of our reach into the cosmos. As the most distant human-made object in existence, the probe continues to travel further into the unknown, far beyond the reach of any other spacecraft. Despite being over 14 billion miles from Earth, this intrepid explorer remains active, sending back valuable data that has reshaped our understanding of the vast, mysterious space that surrounds us. Recently, it appears that Voyager 1 just detected a terrifying object in space. What is this enigmatic object? Why are the biggest and brightest minds of our time so confused? Let's dive in to find out. Discovery of the unknown object. Launched in 1977, Voyager 1 and 2 represented the most ambitious endeavors in the history of space exploration, designed to push humanity's scientific understanding of the outer solar system and beyond. Initially intended to fly past the gas giants Jupiter and Saturn, the spacecraft's journey soon evolved into something much more profound. As it traveled farther and farther from Earth, Voyager 1 became the first human-made object to reach interstellar space, crossing the boundary known as the heliopause in 2012. The heliopause is the region where the solar wind from the Sun, which defines the outer boundary of our solar system, gives way to the interstellar medium, which is the diffuse gas and cosmic radiation that fills the space between star systems. However, this achievement was soon overshadowed by the discovery of an unknown object. As Voyager 1 moved through this uncharted region of space, its instruments detected something unprecedented, a series of unusual signals. This was unlike anything encountered in the spacecraft's prior journey. So, what was it? And what does this discovery mean for us? Have we established first contact with an intelligent civilization, or did we discover a previously unknown interstellar phenomenon? Well, before we move on to the answers, let's get some perspective first. We know that as Voyager 1 passed further into the depths of interstellar space, the strange signals persisted, and the mystery surrounding this whole situation only deepened. In the grand scale of space exploration, this discovery represents a momentous occasion that challenges our understanding of the cosmos. It signifies not only the limits of human exploration, but also the infinite possibilities that lie beyond, waiting to be uncovered. Well, that's brilliant, because wasn't that the whole idea to begin with? The Voyager program. Originally conceptualized as part of the ambitious planetary Grand Tour during the 1960s and 70s, the Voyager mission emerged as a response to a rare planetary alignment occurring once every 175 years. This alignment, identified by aerospace engineer Gary Flandreau at the Jet Propulsion Laboratory in 1964, offered a unique opportunity for spacecraft to utilize gravitational assists, enabling them to explore the outer planets with unprecedented efficiency. Although the original Grand Tour program was eventually shelved due to funding redirection toward the Space Shuttle program, it laid the foundation for the scaled-down but highly successful Voyager mission. NASA repurposed the program in 1972, re-envisioning it as a 2-spacecraft mission derived from the Mariner series. Initially dubbed Mariner 11 and Mariner 12, the spacecraft underwent significant design advancements, leading to their eventual rebranding as Voyager 1 and Voyager 2. The mission's objectives focused on exploring Jupiter, Saturn, and their moons, with additional opportunities for extended studies of Uranus and Neptune depending on mission success. The probes employed the gravity assist technique to achieve the velocity necessary to traverse vast interplanetary distances. This technique uses the gravitational pull of a planet to accelerate a spacecraft, allowing it to gain velocity. Voyager 2 launched first in August 1977, followed by Voyager 1 in September, each embarking on carefully calculated trajectories. Voyager 1's primary goal was a close encounter with Saturn's moon Titan. This precluded further planetary exploration. Voyager 2, however, was designed with flexibility, allowing it to extend its mission to Uranus and Neptune after completing its initial objectives. The Voyager probe's scientific instruments included advanced cameras, magnetometers, and spectrometers, enabling them to capture and transmit invaluable data. Among their many discoveries were the intricate structures of Jupiter's Great Red Spot, the dynamic weather patterns of Saturn, the surprising magnetic fields of Uranus and Neptune, and the peculiar characteristics of their moons. The data collected also reshaped our understanding of planetary systems, providing insights into phenomena such as volcanic activity on Jupiter's moon Io and the icy geysers of Neptune's moon Triton. Beyond their planetary missions, the Voyagers embarked on a journey into the interstellar space. In December 2004, Voyager 1 crossed the termination shock, entering the helioheath, a turbulent region where the solar wind interacts with interstellar particles. Voyager 2 followed suit in 2007, revealing the asymmetry of the solar system's boundary. By 2012 and 2018, respectively, Voyager 1 and Voyager 2 crossed the heliopause, officially becoming humanity's first interstellar explorers. Remarkably, the Voyagers continue to function decades after their launch, relaying data from the fringes of the solar system. However, diminishing power supplies have necessitated careful instrument deactivation over time. Equipped with their iconic golden records, which carry messages of humanity's existence and culture, the Voyager probes are not only scientific marvels, but also ambassadors of Earth. Both spacecraft are remarkable feats of engineering and space exploration. Designed with redundancy in mind, each spacecraft carries 3 distinct types of custom-built computers, 2 of each kind, ensuring resilience in the harsh conditions of space. These systems, built with CMOS and TTL medium-scale integrated circuits and components primarily from the Texas Instruments 7400 series, encompass a total memory capacity of approximately 32 kilobytes across 6 computers. Both spacecraft feature identical systems. At the core of the Voyager's computational capabilities lies the Computer Command System, or CCS. This central controller consists of 2 18-bit word processors, each equipped with 496 words of non-volatile plated wire memory. These processors not only decode commands and manage fault detection, but also handle antenna pointing and sequence spacecraft operations. The Flight Data System, or FDS, comprises 2 16-bit processors, each with modular memory configurations of 898 words. The FDS is responsible for managing data acquisition and processing, including controlling the imaging parameters for the spacecraft's visible light cameras. The Attitude and Articulation Control System, or AACS, ensures the spacecraft maintains proper orientation, pointing its high-gain antenna toward Earth and maneuvering the scan platform for data collection. Communication with the Voyagers involves S-band and X-band microwave transmissions. However, as the spacecraft traverse ever greater distances, data rates have progressively diminished due to the inverse square law governing signal strength. Ground-based improvements, including enlarging the Deep Space Network or DSN antennas and employing antenna arrays, have mitigated these challenges. Powering the Voyagers are 3 MHW-RTG radioisotope thermoelectric generators, fueled by plutonium-238. These generators provided 470 watts of power at launch, though natural decay and thermocouple degradation have reduced this output. Power conservation measures, such as deactivating certain instruments and subsystems, have extended the spacecraft's operational life. The Voyagers transition to the Voyager Interstellar Mission, or VIM, after completing their primary objectives of exploring the outer planets. VIM aims to study the heliosphere's boundaries and interstellar space. So far, key discoveries include magnetic bubbles near the heliopause and the lack of an anticipated shift in the solar magnetic field. Despite subsystem redundancies diminishing over time, both spacecraft continue to deliver valuable scientific data. With adequate power and attitude control propellant projected to last until around 2025, the Voyagers remain humanity's distant ambassadors, venturing further into the cosmos while expanding our understanding of the solar system and beyond. Now, let's take a look at what we have discovered. What did the Voyager probe come across? As Voyager 1 ventured deeper into interstellar space, beyond the influence of the Sun's solar wind, its scientific instruments continued to operate, capturing data on the environment of space in ways never before possible. However, during this unprecedented journey, the spacecraft's plasma wave instrument picked up a series of weak electromagnetic signals that initially defied explanation. The discovery of these signals marked the beginning of an exciting, though bewildering phase in Voyager 1's mission. The electromagnetic signals were weak, but undeniably present. Upon further analysis, it became apparent that these signals were unlike anything previously detected in interstellar space. To understand the implications of this anomaly, researchers began comparing the signals with those of known cosmic sources. Pulsars, quasars, and supernova remnants were among the most likely candidates, as these objects are known for emitting powerful electromagnetic radiation. Pulsars, for instance, produce highly regular and consistent signals due to their rapidly rotating neutron stars, while quasars and supernova remnants are well known for their intense bursts of energy. However, none of these familiar sources match the nature of the Voyager signals. The key difference between the signals detected by Voyager 1 and those from known cosmic sources lay in their random and irregular characteristics. Unlike the steady, rhythmic pulses of a pulsar or the periodic flashes from a quasar, the signals from the mysterious object fluctuated erratically. The data did not follow any predictable pattern, and instead of producing regular bursts, the signals seemed to vary wildly in both strength and frequency. This randomness was in stark contrast to what scientists had come to expect from celestial bodies known to emit electromagnetic radiation. It became clear that whatever was causing these signals was not something typical. The frequency range of the electromagnetic waves was another unexpected aspect of the signals. The majority of cosmic radiation detected by instruments like Voyager's is usually found within certain well-established bands, such as radio waves, X-rays, or gamma rays. However, the Voyager 1 signals spanned an unusual frequency range that was neither consistent with typical radio bursts nor aligned with known radiation from stellar phenomena. These waves oscillated in a spectrum that was not only outside the common range of cosmic signals, but also displayed peculiar, unexplained peaks. Adding to the mystery, these signals did not match any type of radio burst or transient cosmic event that researchers had catalogued. Unlike the well-documented and studied fast radio bursts, which are known for their brief, intense bursts of energy with unknown origins, the signals Voyager 1 detected lacked the repetition that typically characterizes known cosmic bursts. This was one of the most puzzling features of the object. The signals were non-repeating. Fast radio bursts, for instance, occur in repeating cycles, yet these signals from Voyager's unknown object were singular, erratic, and did not recur with any discernible regularity. This feature alone was enough to set the object apart from anything previously encountered. The response from the scientific community was one of fascination, mixed with a healthy dose of skepticism. The unknown source of these signals sparked intense debate among astronomers and physicists. Some theorists began to entertain the possibility that the signals were indicative of something far beyond conventional astronomical understanding. Could this be evidence of a previously unknown type of cosmic object? Or was it something even more extraordinary, such as an alien transmission or an artifact of advanced technology? Others remained more cautious, suggesting that the signals might be a product of some natural, but as yet unexplained, interstellar phenomenon, such as the interaction between Voyager's instruments and the interstellar medium itself. So, what could it have been? Among the various hypotheses proposed to explain the unusual electromagnetic signals, one that stands out involves the concept of strange matter. Strange matter, a theoretical form of matter, is believed to exist under extreme conditions, particularly in the cores of neutron stars or in the environments of black holes. It is thought to consist of a mix of quarks, specifically strange quarks, alongside the more familiar up and down quarks that make up normal matter. This exotic form of matter could possess properties that challenge the fundamental principles of known physics. If this hypothesis turns out to be true, then strange matter could potentially be more stable than the ordinary matter we encounter in everyday life. This stability could allow it to persist in interstellar space, where it might survive for vast stretches of time without undergoing the typical processes of decay. However, the characteristics of this matter are still largely theoretical, and the object's unexpected behavior has led scientists to propose that it could be a relic from the earliest days of the universe. The hypothesis that this object might be a relic from the early universe offers an intriguing perspective. Yet another fascinating possibility that arises is that it might not be a natural phenomenon at all, but rather the product of advanced technology. The idea that the source of these signals could be a technological artifact, perhaps a probe or device left behind by an extraterrestrial civilization, has naturally stirred human imaginations. If this object were indeed an artificial construct, it could be evidence of a highly advanced civilization that predated humanity or exists elsewhere in the universe. The signals emanating from the object could be interpreted as some form of communication, perhaps a form of data transmission, or even an autonomous probe designed to collect information about its surroundings. If this theory holds, it could imply that humanity is not alone in the cosmos, and that the Voyager 1 spacecraft might have unintentionally stumbled upon an ancient artifact from a civilization far more advanced than our own. Alternatively, it could suggest that extraterrestrial intelligence has been exploring or monitoring interstellar space for eons, leaving behind traces of their activity. The implications of this theory are staggering. A technological artifact of such an advanced nature would not only challenge our understanding of alien life and intelligence, but could also spark a revolution in the fields of engineering and physics. It would provide proof that other intelligent civilizations are capable of technologies far beyond our current reach, forcing us to reconsider everything from our approach to space exploration to the very nature of life in the universe. However, some scientists have proposed a more grounded explanation for the unusual signals. They claim that these signals were likely the result of interactions between the spacecraft and the charged particles in interstellar space. As Voyager 1 crossed the heliopause, the boundary where the Sun's solar wind pressure is balanced by the interstellar medium, it encountered a more complex and turbulent environment. The spacecraft's plasma wave instrument detected fluctuations in the plasma, which could produce electromagnetic waves. These signals, while unexpected, were likely due to the spacecraft interacting with the ionized particles in the region, rather than being linked to exotic or unknown forms of matter. Whatever the case, it is no easy task to study this data effectively. We must not forget that the Voyager 1 is over 14 billion miles from Earth. This distance itself presents a host of extraordinary technical challenges that push the limits of modern science and technology. The spacecraft is so far removed from our planet that even the simplest communication with it takes more than 20 hours to traverse the void of space. This delay makes real-time analysis nearly impossible and forces scientists to work in a state of near constant uncertainty. Every piece of information transmitted from Voyager 1 arrives after a significant lag, meaning that researchers cannot interactively respond to the data or adjust the spacecraft's instruments based on immediate findings. Instead, they must rely on highly methodical and anticipatory strategies to gather insights. Even a seemingly minor error in planning or data interpretation can set back the entire mission by days or even weeks. The technical limitations of Voyager 1 itself compound these difficulties. Launched in 1977, the spacecraft was not designed for deep, long-term interstellar exploration, and its instruments were intended for a much different mission, to study the outer planets of the solar system. While Voyager 1's capabilities were cutting-edge at the time of its launch, they have significantly diminished due to the inevitable wear and tear of nearly 5 decades of space travel. Over time, key systems and instruments have experienced degradation or are functioning at reduced efficiency. For instance, its power source has been gradually losing output, limiting the amount of energy available to power its onboard instruments and communications systems. As a result, many of the probe's scientific instruments can no longer operate at full capacity, and the data it transmits is not as detailed as scientists would prefer. While this may be disappointing for now, it is not a failure. We now know that the interstellar space houses the unknown. What we need now is a renewed and more effective approach. Voyager's legacy and humanity's place in the universe. Voyager 1 stands as one of the most extraordinary achievements of human ingenuity, a testament to our species' insatiable curiosity and unyielding determination to explore the unknown. As the spacecraft probes the mysteries of interstellar space, it forces us to confront our own smallness in the grand cosmic landscape. Are we truly alone? If so, then life indeed is an anomaly rather than the norm. But if life exists elsewhere, how does it compare to us? If we were to stumble upon some solid proof, we'd have to reevaluate our position. We would then not be the masters of creation, but participants in a vast, interconnected expanse of existence. Voyager 1 carries with it a message of humility. Despite our technological advancements, we remain explorers on the periphery of understanding. The potential for encounters with extraterrestrial life or advanced technologies looms large in the context of Voyager 1's journey. Its presence in interstellar space opens the door to questions about what lies beyond. What other worlds, civilizations, or phenomena might be waiting in the unexplored reaches of the cosmos. But wait, we actually prepared for such an eventuality. If an intelligent life form were indeed to come across this spacecraft, they would be greeted by a record of Earth, encoded in the golden record affixed to its frame. This time capsule, featuring sounds, images, and greetings from humanity, was designed to communicate the essence of life on Earth to any potential extraterrestrial recipients. It is a hopeful gesture, a recognition that even as we extend our reach into the stars, we are inextricably tied to our home planet and the diversity of life it sustains. The golden record is both a celebration of our achievements and an invitation to the universe to know us. So, what comes next? A vision for the future. Though celebrated as a monumental achievement in human exploration, Voyager 1 is nearing the limits of its endurance. Launched over 4 decades ago, it continues to function remarkably well for its age, transmitting data from beyond the solar system despite its diminishing power supply and outdated technology. Its ability to detect and relay mysterious signals from billions of miles away is nothing short of extraordinary, but its limitations also underscore the necessity of advancing space exploration technologies. As Voyager 1 approaches the twilight of its mission, its discoveries serve as a reminder that while it has paved the way for interstellar exploration, it is not equipped to answer the profound questions it raises. Future spacecraft must incorporate cutting-edge advancements in propulsion systems, energy efficiency, and communication technologies to navigate the vast distances of interstellar space more effectively. For instance, solar sails, nuclear propulsion, or even theoretical concepts like warp drives could enable future missions to achieve greater speeds and reach previously inaccessible regions of the cosmos. Additionally, advanced instruments with higher sensitivity and broader spectral ranges could provide unprecedented insights into the signals and objects encountered beyond the heliopause. One of the most ambitious goals for the future of interstellar exploration would be the development of missions capable of returning samples from beyond our solar system. Such an undertaking would be an engineering challenge of immense proportions, requiring breakthroughs in autonomous navigation, long-term reliability, and sample containment systems. However, the potential scientific payoff is staggering. If we could analyze material from an object like the one Voyager 1 detected, it might revolutionize our understanding of the universe. Samples could reveal details about the object's composition, its physical and chemical properties, and possibly its origins. They might even contain clues about processes or phenomena that are entirely unknown to modern science. Just imagine how many new fields of study would be born from this. These advancements would not only deepen our knowledge of the object, but could also provide a framework for addressing larger cosmic questions. What materials and forces shape the universe beyond our solar system? How do these factors differ from the conditions we understand? Could such objects harbor signs of life? Or do they represent phenomena that challenge our current understanding of physics? By bringing tangible pieces of the cosmos back to Earth, future missions could transform abstract signals into concrete data. In addition to technological innovations, future exploration efforts will require a collaborative, international approach. As space agencies and private companies worldwide develop their capabilities, pooling resources, expertise, and funding will be crucial for achieving the ambitious goals set by Voyager 1's legacy. The creation of interstellar exploration programs that unite nations could inspire a new era of scientific discovery and global cooperation. Furthermore, public engagement and education will play an essential role in sustaining the vision for interstellar exploration. Voyager 1 captivated the world with its iconic pale blue dot image and its daring journey into the great beyond. Similarly, future missions must aim to inspire the same wonder and curiosity in new generations, ensuring that the spirit of exploration remains a driving force for humanity. As we look to the future, Voyager 1 serves as a beacon, illuminating both the possibilities and the challenges of interstellar exploration. While the spacecraft itself may not last forever, its legacy will endure. The discoveries it has made and the questions it has raised remind us that exploration is an ongoing journey. The vision for the future is clear: to reach farther, to understand deeper, and to continue the quest to unravel the mysteries of the cosmos. In doing so, we honor not only the achievements of Voyager 1, but also the boundless potential of human curiosity and ingenuity. And there is so much more to explore. For example, the source of the signals itself. cosmic rogue, a new perspective. According to some experts, the enigmatic signals detected by Voyager 1 may be coming from a cosmic rogue, or an object wandering the vastness of space without a definitive stellar or galactic origin. Such rogue entities defy the conventional understanding of celestial bodies, which are associated with a parent star, planetary system, or galaxy. Unlike planets tethered to stars, or stars bound within galactic clusters, cosmic rogues are nomadic by nature, adrift in the cold, dark voids between known celestial structures. Rogue objects challenge traditional cosmology by suggesting that the universe harbors a population of unanchored entities, possibly ejected from their original systems due to gravitational interactions, violent cosmic events, or unknown processes. Studying these objects could illuminate aspects of the galaxy's tumultuous history, offering insights into events such as supernova explosions, black hole interactions, and galactic collisions. Each rogue object might carry a unique story encoded in its composition, motion, and energy signatures, acting as a time capsule from a distant past. One of the most intriguing aspects of rogue objects is their ability to survive in the extreme conditions of interstellar space. Without the warmth of a nearby star, these entities endure temperatures nearing absolute zero, bathed only in the faint radiation of distant stars and the cosmic microwave background. Investigating how these objects persist and retain structural integrity in such a hostile environment could advance our understanding of material science, thermodynamics, and the limits of life-supporting conditions. Furthermore, the study of cosmic rogues could provide clues about their origins. Are they remnants of failed planetary systems, chunks of matter ejected during violent stellar deaths, or even fragments from primordial cosmic events that predate star formation? Analyzing their compositions could reveal whether they still bear traces of their original environments, such as star-like isotopic signatures or remnants of atmospheric elements, providing direct evidence of their formation and evolution. When Voyager 1 detected the aforementioned signals, it opened up the possibility that the object's unusual electromagnetic emissions and unpredictable behavior could be linked to ancient supermassive events like hypernovae or interactions with dark matter. Alternatively, such objects might represent a new class of celestial bodies that exist independently of current astrophysical models. The discovery of rogue objects may also open the door to identifying entirely new types of celestial phenomena. For centuries, our understanding of the universe has been shaped by observable entities like stars, planets, and galaxies. Rogue objects, with their unorthodox characteristics and behaviors, challenge this paradigm by existing outside the expected boundaries. Their study could uncover processes and forces that do not fit into established scientific theories. Finally, the implications of studying cosmic rogues extend beyond pure science, touching on humanity's philosophical and existential questions. These solitary travelers, moving silently through the void, reflect the vastness and mystery of the cosmos itself. They remind us that the universe is not static, but a dynamic, evolving entity, filled with wonders yet to be discovered. As we delve deeper into their secrets, these lone wanderers may hold the key to unlocking some of the most profound truths about the cosmos. But wait, there's more. Dark matter, new theories and possibilities. It is also possible, at least according to some experts, that the Voyager 1 detected dark matter, an elusive substance believed to constitute approximately 27% of the universe's mass energy content. Despite its prevalence, it remains one of the greatest enigmas in modern astrophysics. It has also evaded direct detection. Dark matter's role in the universe is both pervasive and enigmatic. It is hypothesized to act as a gravitational scaffold, binding galaxies together and influencing their rotation. Without dark matter, current models suggest galaxies would lack the mass necessary to remain cohesive. If future studies reveal that the source of the Voyager signals exhibits properties consistent with dark matter, such as weak or non-interacting behavior with electromagnetic radiation, it could confirm theories about the existence of dark particles, or exotic substances like weakly interacting massive particles or axions. Identifying these properties might also provide insight into whether dark matter interacts with itself or other forces in the universe. Such interactions, if observed, would represent a paradigm shift in our understanding of fundamental physics. Moreover, by understanding dark matter's properties, scientists could refine models of galaxy formation and the universe's large-scale structure. It might illuminate how galaxies coalesced in the aftermath of the Big Bang, offering a clearer picture of the processes that shaped the cosmos over billions of years. Moreover, investigating the potential link between the Voyager detected object and dark matter could shed light on previously unexplored regions of interstellar space, where dark matter's influence might be observable. Whatever the case, the future of exploration is as promising as ever. We must not give up now, but rather amp up our efforts to make history yet again. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.